So like when you switch pairs of reactants, so metathesis is exchange, so like whenever we have solution A, solution B, where they're both ionic compounds, we're thinking, can we switch the metal ions around? And the question there is, do I get a solid precipitate? So you have to have one of the two products be a solid, otherwise it's no reaction. And so the idea would be for, does a metathesis or exchange reaction occur, would be when you take two aqueous solutions, do we mix those and get a solid precipitate? If so, then you have a reaction that can take place. Otherwise, the answer would be no reaction. And then the other case would be, can you take like calcium solid and dissolve it into copper ion solution there? That becomes an activity series question where yes, you can do that because calcium's higher up on the chart. Calcium's less reactive, calcium's more reactive, it's higher on the chart. Copper's less reactive, so they swap, if you will. Charge states, they don't change positions. We're not like changing positions per se. We're kind of almost imagining the one giving electrons up as the other accepts the electrons. But then if you flip it, if you say copper solid into calcium ion solution, no reaction there. So I think chapter 4, we're just thinking metathesis, precipitation. We need something to form a solid using the solubility chart. Acid base, we just need there to be an acid or base. And it's just a question of we need at least one of them to be strong. So we need at least a strong acid or strong base to be present. The other can be weak. And then from there, we need to think activity series for oxidation reduction. Okay, so into chapter 5 kind of, in some ways changes gears a little bit from just getting at different reactions and trying to learn what we can learn about different categories of reactions, gets into kind of, well, what can we learn about the energy changes that accompany a chemical reaction? So chapter 5 is on thermochemistry. And so it talks about the nature of chemical energy, the first law of thermodynamics, that we're not creating or destroying energy. We're just changing, maybe potential into kinetic or vice versa through reactions. We introduce topics, if you haven't seen them before, like the enthalpy is the heat change that accompanies a reaction. So if A is going to form B, is heat gained or lost in the process? Now, it turns out that for a reaction that occurs without external forces, we call that spontaneous. So for a spontaneous reaction, it can actually lead the reaction to either absorb heat from the surroundings or give heat off to the surroundings. So we can find examples, and we'll show you some examples like in person with a demo next time, but we'll see examples of reactants that we can mix together where heat's evolved from the reaction, where the sort of temperature that surrounds the reaction goes up, and we can do the opposite. We can have a reaction take place spontaneously that we can see and know that takes place, and then the reaction gets cold. The water takes place and starts losing its heat because it's being lost to the reactions that takes place. So the change of this reaction, the delta H sign, you may have seen this before, the enthalpy change for the reaction can either be less than 0, the delta H could be exactly equal to the 0, or the delta H can be greater than 0, and the reaction could still take place. So in other words, we can have reactants that absorb heat, give heat off, or have no heat change at all, and all three of those possibilities can be examples of reactions that are allowed to take place. What I'm trying to show you here is that the delta H is not the thing that tells you if the reaction can take place or not take place. If you learned a lot of chemistry in high school, you may have learned about Gibbs energy. Delta G is the equation you would want to know. If that one's negative, the reaction can be spontaneous. If it's positive, the reaction's not spontaneous. So the idea, can the reaction take place without external forces acting upon it? That would be delta G. We don't talk about that in chemistry until chapter 19. So it's not for quite a while in the book that you get to that topic, but you may have learned or heard about it before. But it's important for me to make sure that we're all of the mindset that the delta H is not the thing that determines if the reaction can or can't take place without external forces acting upon it. The thing that you would know is delta G. So you might be remembering there is a, if you will, state function or a function that can tell you about spontaneity. That's delta G. You'll learn about it later. And so we'll talk about in this chapter how we know what we know about enthalpy, how we can track delta H's of reaction. We'll get into calorimetry as a way of determining delta H's. So a lot of the enthalpies of reaction we know have been studied and determined through calorimetry experiments. You'll do a calorimetry experiment in the lab as well. We'll talk about Hess's law, which is in a way of restating of like the first law of thermodynamics. But this will be how we can take a series of reactions and kind of like add them up and then be able to add the enthalpies up. We can even do a very simple example today. It's kind of like if A to B has a heat change of, say, plus 10 kJs. So if in order for A to turn into B, or whatever the reactants are to convert to their products, if that's plus 10 kilojoules, so in other words, 10 kilojoules of heat has to be absorbed to form B. And then let's say once you get B, you can then get to C, and then that reaction has a delta H, let's say, of minus 30 kilojoules. So you get B now all the way down to C is minus 30. This allows you to kind of start like making a diagram where like A to B goes up by 10, and then to go to C goes down to minus 30. And then the A to C reaction, we should be able to add these two reactions up. If we add these up, the B cancels itself out, or the energy of B versus the energy of B on both sides of the reaction cancels out. So our A to C should just be, since we've added up the reactions, should just be the sum of our delta H's. So the delta H here would sum up to be minus 20 kilojoules, just taking 10 minus 30. So it's like if A to B's up by 10, if B to C is down by 30, then A to C should be down by 20. And so that's the basic idea of what Hess's law is. And so I just bring that up here because we probably can imagine or comprehend or put that into practice even here at the very start of the chapter. We then get into what we call enthalpies of formation. So we can start to tabulate for substances, what's some value we can determine experimentally that then allows us to sort of plug into an equation. So what if we could find for a bunch of different reactants and products a way to tabulate their standard enthalpies so you can just take the sum of the products minus the sum of the reactants and get your delta H. And so we'll get into that topic towards the end of the chapter. And then one of the more important topics to me, because this allows us to try to start to comprehend why reactions involve heat changes, is that the reason why we see an enthalpy change during a reaction just has to do with the nature of the bonds we're forming. If we start with very weak bonds and we form very strong bonds, then we have heat that can be evolved. That's like the H2O2 reaction. We blew up that balloon. Must have meant that we must have had some weak bonds because they were just like they were just waiting for a spark so that they could start breaking and then allowing those bonds to reform stronger bonds. We make strong bonds, then they're forming bonds that are more stable. They're not likely to react to form other things. And then when they form, that there's an energy difference from those weak bonds. And that's the energy that we saw given off was the energy difference from the weak bonds from the stronger bonds. So it has to do with when we see reactions that give off a lot of heat, that they must involve generally having weaker bonds and then producing stronger bonds. The energy difference is what we see given off in the form of a flame or explosion for those reactions. So bond enthalpies will help us understand that. Okay, so the nature of chemical energy, we have a few different equations that we'll just try to like comprehend a few things from these equations, not even so much for using these to solve problems just yet, but the idea of work. It's the energy required to put objects into motion. So work is a force applied to move an object a certain distance. And so force is equal to a mass times acceleration. Now again, I'm not trying to show you these equations so we can start plugging numbers into them, but just to think that if I'm going to move an object, then energy has to be applied to the object. That energy is what we call work. And so the work is the energy required to put objects into motion. Heat is the sort of equation or relationship for the amount of energy it takes to change an object's temperature. And so Q is equal to MCS delta T. We will use this equation later in the class, not so much today, but this idea is just the idea that if we have an object, we have some quantity of it, and we want to raise its temperature, then heat has to be applied to the object. So we have to have something that allows the object to heat up so it can increase its temperature. If we want to decrease the temperature, we have to take heat away. And so applying heat to change the temperature upward or taking heat away to reduce the temperature is the idea from the heat equation. And then we have the electrostatic attraction, or just the electrostatic equation that kind of tells us about attraction. So this equation here is saying that the electrostatic force between two particles is related to a constant that we never really talked too much about, but a kappa constant, and then Q1, Q2 times D. And what Q1 and Q2 are, you could imagine this being, it could be like a nucleus, and then you have an electron negative particle attracted to the nucleus. And so you can think of, I have a positive particle, I have a negative particle, and there's some distance separating those particles. And so this law here, we call this Coulomb's law. It's just the law of the relationship between the particles. And of course, you want it to be plus and negative in order for this force to be attractive. If you took two negative particles, they would have repulsion. If you took two positive particles, they would have repulsion. So you don't want plus plus or minus minus because those would involve repulsion. And there's a slide, I think the very next slide will show us an example of electrostatic potential energy where it's attractive when they're opposite in charge and repulsive when the charges have the same charge. Yep, so that's this slide here. So this slide here is showing us that if we take two like charged particles, so imagine plus plus or maybe it's minus minus, that if the particles are introduced together, their energy increases. So we increase the potential energy of particles that have the same charge. Another thought would be if you could somehow bring two positively charged ions together, if you could release them, then they separate, then you would reduce their potential energy. So if you're picturing two particles that have been brought together, then it would be a good idea to separate them because then they could release energy through their separation. And then the opposite could be true, and the axis here on the x-axis is the distance of separation. So imagine a plus and a minus ion far away from each other. If we introduce them close together, then they can drop in energy as they experience that attractive force together. And so the oppositely charged particles now drop in energy. They have an electrostatic potential energy of attraction. And then they get as close as they can get together, but not infinitely close because eventually these two atoms have nuclei. The nuclei are positively charged, so the ions can't just overlap each other, so they get some distance away from each other. We'll talk about like sort of size of ions and how big cations and anions are when we get to chapter, I think, 7 later. So we'll talk about the relative sizes of ions as we get into some later topics. But the idea here is that plus minus attractive, they reduce in energy, they have an attractive force. The two positive particles have a repulsive force. The two negative particles have a repulsive force. Okay, so how does this apply to some chemistry examples? So one of them is that if you look at the H2O2 reaction where you're combusting the balloon, blowing up and kaboom, you remember the first day of class. If you didn't get a chance to see that, there's a video of it up there at the very start of the class. But we have that stored energy in the bonds of hydrogen and oxygen that can be released as we're forming water, which is what we were talking about earlier, just apparently more stable. So we're starting with something that's more reactive and producing something less reactive in the process of making water. And it's that energy difference here. And you could sort of have imagined that the energy must have been released from this reaction in order for us to have witnessed and seen that big explosion. So it would be hard to imagine the reactant water absorbing energy, because how would it absorb energy if we saw the big explosion? Like the explosion was us seeing the heat given off in the form of that fireball. And so here we have H2O2 as our initial state, higher in energy, producing water, lower in energy. This becomes kind of a potential energy problem where H2O2 at the top of the hill, water's at the bottom of the hill, and then we have that energy given off as we just give a little push, the little spark to the reaction is a little push for that reaction to take place in order to produce the products. And so, so what we have here is we have two different types of reactions that can occur, and either one of these could be spontaneous depending on the nature of the reactants. But generally speaking, a reaction that's spontaneous in one direction is usually, if you flip it, not spontaneous. Let's change gears for a minute here. Let's think oxidation reduction again. So when we had like the idea of calcium metal dissolving in copper ion, that being a reaction that can take place, that's spontaneous. That means it can take place without us acting up. We just put the piece of calcium in the solution of copper ion and it reacts. If we do the opposite reaction, if I take the copper solid into the calcium ion solution, no reaction takes place because that reverse reaction is not spontaneous. So the forward reaction for, let's even write this out to make sure that we're all picturing the same thing, that calcium solid can react with copper 2 plus ion to produce the calcium 2 plus ion plus copper solid. And then these ions are in water aqueous. And so this reaction is spontaneous. Now, if you flip the reaction and say, well, what about the opposite reaction? What about calcium 2 plus the copper solid, which is the thought of putting a piece of copper into the calcium solution, that this goes to no reaction. So if we know the one direction of a reaction is spontaneous, if you flip the reaction, then that should be non-spontaneous. And so the whole idea here would be that for a given reaction, it could be that a given reaction is one like water where heat's given off. That would look like this case here. So if heat's given off, then that reaction being spontaneous in that direction would allow the reaction to give heat off to the surroundings. We could also have a different reaction take place where heat's absorbed. And then if heat's absorbed by the reaction when it takes place, then that would be an example of a reaction that's absorbing heat from its surroundings. And so you can imagine that probably giving heat off is better, and that if you get to chapter 19 later, you'll see that a reaction that loses heat, that gives heat off, is productive towards making that delta G term be spontaneous. But there is another element called entropy that we're not talking about, this order of the system. And so once you put that together, it allows you to predict spontaneity. But the idea here is that some reactions will be spontaneous that allow the reaction to absorb heat and be the opposite type of reaction as that of water. These reactions we would not expect to take place with a big boom or a big burst of fire. This is a type of reaction that would be pulling heat in from the surroundings. So when we start thinking of reactions, we get to an equation that we can use or relate to, that the energy change of a reaction, the delta E change, is related to the heat change of the reaction or the work change of the reaction. So let's rewrite this equation here. And sometimes I like to throw these tags in, like the delta E is equal to the heat change of the reaction plus the work change of the reaction. And this gets us into a discussion that a reaction, like let's imagine the combustion of octane in your car engine. Like imagine a particular reaction taking place, one that we know of that gives energy off. So we know just from the nature of how we use octane, that octane burns to give energy off. And we can use that energy for two primary purposes. One could be that before you start your car, first thing in the morning, your car engine's probably cold. And then you start the car and eventually don't touch it to find out, but eventually the car engine gets hot. And so the combustion reaction here is giving heat off to the surroundings, and the surroundings, the engine block, are increasing in their temperature. And so if we imagine the delta E that's less than 0, that means energy is being given off by the reaction. And so energy is lost by the reaction. Now, it's not lost to nothing, it's lost to its surroundings. And so we have here a reaction we know is losing energy, and then our Q reaction would be less than 0, and this would imply that heat was released by reaction. And so for this reaction that we're thinking about here, the octane in a car engine being a reaction that releases energy, that reaction, the way we know that we use that reaction is that the reaction loses heat to the surroundings. So the heat's lost by the reaction. Where does it go? It goes into the engine block. So the engine block increases in its temperature. So the energy goes to the surroundings. That heat that the reaction loses goes to the surroundings, warms up the surroundings of the combustion reaction. So you have octane burning in the car. It makes the surrounding engine hotter because the heat was released to the surroundings. And then what about the sign of W? So the car's moving, so we're using the octane to actually move the car. So we're in drive, the car is moving and accelerating, while we're applying a force to move that car a distance. And so that's where work comes into play. Like if we're actually applying a force onto that object, allowing it to move, that's using some of the energy of the reaction to put the car into motion. And so here means that work was done on the surroundings by the reaction. Okay, so again, for this reaction, now this discussion here is kind of complicated because we're not saying when delta E is negative that the Q has to be negative and W has to be negative. What we're trying to say is if we're picturing a type of system where we know the reaction is known to release energy, because that's why we're using octane in the car, is to take the energy given off, so that we can either warm the car up, which is probably not what we really want to use the reaction for. We want to use the reaction to power the car, to move the car. To move the car takes work, so the engine has to do the work so that the car can receive the work. So the car moves, the car receives the work. Where did it come from? It came from the energy that was given off by the reaction. So now let's imagine a reaction where, let's just say delta E is minus 100 kilojoules. What that means is I have 100 kilojoules that I can give to the surroundings either in the form of heat or work or the combination of the two. And so what we can do is, like, let's say Q can be equal to minus 10 kilojoules. So that means that the car receives 10 kilojoules of energy that was lost by the reaction. And then that would have to mean that W was equal to minus 90 kilojoules. So if the engine has 100 kilojoules to lose, then let's say, for example, maybe the engine's absorbing 10 kilojoules, and then the car itself absorbs the other 90 kilojoules in the form of pushing it down the street. So we give it a certain force so it can accelerate to a certain distance. And now again, we're not going to work out the W is equal to force times distance problem for the mass times acceleration. We're not going to get into the physics of it. We're just trying to get into the understanding that the reaction can heat something up and it can move something. And we're trying to understand the sign conventions for what it means to lose energy, to lose heat, to put an object into motion. Okay, now delta E turns out to be something we call a state function. So delta E is whatever it is. Like whenever you have a certain quantity of octane burn, has so much energy it gives off. Now, we could have all of that energy be given to the form of heat. Like, for example, put your car in neutral. I don't recommend doing this, but if you put your car in neutral and put your foot on the accelerator pedal and the engine revs up, where does all the energy from that combustion reaction go? I can't go into moving the car because work has to be zero. The car's not moving anywhere. And so work is effectively zero. So all the energy given off by the combustion reaction is going to the engine block and it's going to heat up. So eventually you put your foot in the accelerator pedal, the car's going to blow up at some point. The engine's going to break. So you're going to melt the engine from all the heat being given into the engine. So obviously don't do this. But the idea is there's a way we can run this reaction with the car in neutral where almost all the energy given off by the reaction goes into Q. Now, if we take our foot off the accelerator and we accelerate down the road to as much as we can accelerate, then we're probably having as much of the work being done as possible. The car engine's still going to heat up. So we might have a small amount of heat, but we can have a lot of work being done. So Q and W depend on how we're using the reaction, but delta E itself is just determined by the nature of the reaction. And this comes up again on another slide later, but delta E we say is a state function, path independent. Q and W are path dependent. It depends on how we use the reaction. Now the sum of Q and W is limited by delta E, so Q and W can't just be anything, but they depend on how we're going to use the reaction. So you can imagine that we could be in neutral, we could be in drive, we could be totally on the accelerator, a little bit on the accelerator. Depending on those variables, we have a variable amount of Q and W that are being received by that reaction. Now let's look at this side here, trying to get into some of the sign conventions so we can think, what does it mean to be delta E positive versus negative? And we went through just all of these. So like the example, that reaction we just looked at, kind of went through what it would mean to have a negative or a loss of energy by our system. We looked at having a loss of heat by the system and a loss of energy through the form of work being done by the system on the surroundings. And so let's go through this one more time for the negative side. And so the idea here, let's look at E first. And so a net loss of energy by the system to me is usually a reaction. So early on in chapter 5, a lot of times we talk about system versus surroundings. And I like to think of it as like a chemical reaction occurring in some sort of a container. We'll talk about different types of containers in a few moments, but we have like a reaction generally is our system. And so system, kind of like thinking of our reaction. And so here we're thinking delta E negative just means that our reactant is here, picturing A to B, so that would be A here, and then B is down below in our energy scale. So if B is losing energy, if B is more stable, then that's delta E negative. That's our combustion reaction of octane. And then the The Q being negative means heat is, the system loses heat. Where does it lose the heat to? To the surroundings. So the surroundings receives the heat that's lost by the reaction. And the same thing, if the reaction releases work, if the reaction uses its energy to power something into motion, that's the W being negative by the system. So the work sign for the system is negative. And where does the work go to? It goes to moving the surroundings. So we're kind of thinking here, we have a system, we have the surroundings. And this is a complicated thing. We'll have to talk in a minute about different types of systems. But for a mechanical system, this is really complicated. Any mechanical engineers in the room? If you're like ME, this is probably like a big thought of the Q versus W. I mean, you're really trying to make Q as small as possible, W as big as possible in most of your mechanical systems. This is a chemistry class. We're eventually trying to get to a chemical system, which is going to be a flask with something in it, an open container, or it might be like a sealed up calorimeter cell. We'll talk about those as we get into some different units. But the idea of a chemical system is going to be, we're just trying to do chemical reactions. So what we're going to do in chemistry is we're really going to try to make work pretty small or almost negligible so that we're not really powering objects with the types of systems we want to talk about. Because what we want to try to do in this class is just try to determine energy changes of chemical reactions in some sort of like chemical system. So we're really going to be trying to make work small, but we really want to make sure we understand what work is here. And so work is the energy required to move an object. So W is negative for our system. We're putting an object into motion. Now, what does it mean for delta E to be positive? For delta E to be positive, let's picture a different reaction. C goes to D. If C is here and D goes uphill, then D has to go through the process of absorbing energy in order to be produced. And so if this is what our energy looks like here, this is our energy being greater than 0. So C has to absorb energy in order to form D. Now, the good news is that reactants can absorb energy from their surroundings. So we can take energy, if we're in a solution, we can take the energy from the solution. We could heat the solution up. So maybe in the lab, the way you would generally do this is you would like physically heat up your mixture so it can take the heat to produce the product. You don't necessarily have to heat a mixture. We'll see next time that you can put some different compounds in the water that lead the temperature to drop. Other types of compounds lead the water temperature to increase. And both of those reactions that are occurring in water occur without external forces, occur spontaneously. So again, delta E greater than 0, this can be perfectly spontaneous, meaning reactions can absorb energy as they take place. And then what has to be the case is that either they absorbed heat from their surroundings, and so the Q sign for the reaction, if it's positive, means that a Q positive means that the system is gaining heat from the surroundings. So if Q negative is releasing heat to the surroundings, Q positive is absorbing heat from the surroundings. And so Q negative, you give heat to the surroundings goes up in temperature. So in the negative case, the surroundings temperature should increase. But in the positive case, this maybe seems not so intuitive, but if you think of a reaction that's absorbing heat, where does the heat come from? It comes from the surroundings. The surroundings temperature should be dropping if we have the Q sign positive. So the reaction's absorbing the heat, but the surroundings are where the heat's coming from. The surroundings heat's dropping. So if you take heat away from the surroundings temperature drops. A thought here would be, if I'm putting a thermometer on something, it's probably the surroundings. Think about this for a minute. Like if you have an A goes to B, how can you put a thermometer on that? Because A was there once the reaction takes place, now B is there. It's pretty hard to put a thermometer onto something that was there that isn't there versus something that is there now that wasn't there before. It's really hard to put a temperature on the reaction. It's much easier to put a temperature onto what the reaction's in contact with. It's much easier to put a thermometer onto the surroundings of the reaction mixture. So if you have the reaction occurring in water, you're tracking the temperature of the water that surrounds the reaction, not the reaction itself. So just have this in the back of your mind that if we start talking about temperature, it's almost always of the surroundings of the reaction, not of the reaction itself. And so whenever we start thinking about temperature, it's usually and almost always going to be of that surroundings. And so then what does W positive mean? It means that work is being done on the system by the surroundings. And so the same idea here, W positive means that work is being done on the system by the surroundings. Now, this is kind of hard to imagine what this means because it's pretty hard to, picture a reaction that's being done specifically by like the deceleration of the object. But that's what this is really getting at. It's either the system decelerating, or it could be like it could be like a contraction of the number of moles of gas as the reaction takes place is another way of thinking of this. But it's just somehow the surroundings moving inward onto the system. And if you think of the opposite, let's think of what W positive means. If you think of like, what does it take to push our surroundings? Usually like an explosion that pushes the surroundings. So imagine you have, say, a piston and a reaction taking place. So if the reaction takes place and it drives the piston upward, that's us moving the surroundings out of the way. So that's the W negative. So then if you imagine the opposite, we have a reaction take place that pulls the piston inward, then that's going to be the opposite sign. That's the W positive. So that's now the surroundings moving inward onto the reaction. So in a lot of ways, work is the trickier term to consider here, although I think putting a car into motion is pretty easy to conceptualize. So I think the negative W is pretty easy to conceptualize, the positive W a little harder. But the good news is we're trying to really make W go away. We're going to try to really not so much talk about work because we're going to want to get into chemical systems where work is going to be either negligible or even zero. Okay, so let's look at a couple questions here. So we have an internal combustion engine, use to power hydrocarbons such as octane to put automobiles into motion. What's the sign of delta E, Q, and W? We kind of went over this already. So the sign of delta E, just from the nature, the idea, I think, just like stating this again, is just from our knowledge of how octane burns, like with a flame, that we know we put it in our car to power it. That's how we know that the energy of the reaction must be releasing energy as it takes place so that we can use that energy to power the car to heat it up. And so the delta E of our reaction is less than zero. And then we know the car engine can be warmed up through the process of using the combustion reaction, so the Q reaction, less than zero. You can think what that means for the surroundings heat is that the surroundings gains the heat lost by the reaction. We can maybe introduce this idea here that the Q reaction, the heat change of the reaction, is the opposite sign of the surroundings. So any heat lost by the reaction doesn't just disappear, it goes to the surroundings. And so if a reaction's losing heat, that means the surroundings gaining the heat. And that means that the temperature of the surroundings should increase. So like, not a good idea, but if you do the combustion reaction of the balloon, I'm sure if you put your hand in front of the balloon, you would feel it get hot. It seems like a pretty good prediction that you would feel the heat being given off by the reaction. And so the way you can think of the thermodynamics working would be the reaction releases energy in the form of heat, and then you become part of the surroundings if you were to absorb the heat through your hand to feel the temperature. So you would just be feeling your hand as part of the surroundings, increasing in temperature as a result of that temperature taking place, or that reaction taking place. And then if we're powering the car to move, work's being released in the form of, energy is being released in the form of work to move the car. And so W is negative to put the car into motion. And then the surroundings would be greater than zero here because the work released by a reaction go to the surroundings. Just like Q. So if we're releasing work, if work is done by the system, it's done on the surroundings. So the surroundings receives the work that was released by the car. And so the car is moving and moving faster as a result of receiving the work that was released by that chemical reaction. I should say that some reactions you can't just look at and determine the delta E sign. If I just put up a random reaction and just said, okay, for this other random reaction here, what's the sign of delta E? What's the sign of Q? What's the sign of W? That we couldn't predict those. Like, it's just our understanding of what we know about cars, what we know about the what we put into cars to allow them to move. It's our understanding of that reaction that we know of that allows us to determine these signs here in this problem. Let's also talk about another thing, that the hydrocarbon combusts. We know that reaction, right? That's one of our chapter 3 reactions, that our hydrocarbon, like a C8H18 is octane, that burns with O2 to produce CO2 and water. So like a chapter 3 question would be, what are the products of the reaction, CO2 and water? So presumably CO2 and water more stable are hydrocarbon up here, just like the H2O2, high energy, the product's lower in energy. Okay, so what about some random numbers here? So what if we have a delta E of a system that absorbs 22 of heat, what is the delta E of a reaction or system that absorbs 22 kilojoules of heat from its surroundings while doing 45 kilojoules of work on its surroundings? Let me throw this to you guys for a minute or two. And this is about sign conventions. This is about trying to figure out, should Q be positive or negative here? Or should W be positive or negative? And then once you know their signs, you should be able to sum them up to get delta E. So take maybe 2 minutes here. All right, let's take a look at this one. So the first thing that I was thinking here is just making sure that when we see this equation, delta E is Q plus W, that we're either thinking that it's a delta E of our system, is the heat change of the system plus the W change of the system, but the system's usually a reaction, so I can write the same equation as basically that the system and reaction are mostly interchangeable to each other, and so delta E reaction is equal to Q reaction plus W reaction. We could also probably write delta E surroundings is equal to Q surroundings plus W surroundings, but we tend not to really think of delta E of the surroundings. This would just be a weird way, I think, of thinking through. So the delta E of our reaction is usually what we want to know. It's the sort of, whatever the reaction is, like A goes to B, it's like for that reaction of whatever the reactants are to the products, is that energy being absorbed or released by the reaction? That's our delta E. So we want to know the delta E for some reaction here. So that's the reaction, just a generic one under consideration, just whatever the reactants are turning into the products. And then the sign magnitudes would be that if heat is being absorbed by the reaction, that's positive. That's Q being absorbed by the reaction is positive for the reaction. If heat's being released by the reaction to the surroundings, then that's negative. And so if we at least remember one of the directions, we can remember the sign convention here, that heat being absorbed by from the surroundings by the reaction is positive. So that's plus 22 kilojoules. If you thought that was negative 22 kilojoules, I just think that negative 22 kilojoules would be heat that was released by the reaction to the surroundings. So the heat being absorbed from the surroundings to the system is plus 22 kilojoules. And then the system doing the work, if we release energy in the form of work, is the system moving the surroundings, the system working on the surroundings, then that would be negative. So the work is negative here because it says that we're doing 45 kilojoules of work on its surroundings. If the surroundings is doing work on the system, then that would be positive for work, but work. So I like to think of if we heat up the surroundings, that's the heat being lost by the reaction. If we also think heat outward, if we think work outward, move the surroundings, that's also W negative. So just trying to get the sign conventions for Q versus W down here. So our Q is plus 22, our W negative 45. We're just adding those up to negative 23 kilojoules is our delta E sign. Now, just random numbers here. Like the idea of this problem here is if you just knew Q and W, you can plug in for delta E. So if you know 2 of the 3, you can solve for the third. There's no rhyme or reason here. It's hard for me to give you an example of a reaction that might be capable of producing these numbers. It's really hard to come up with like a physical picture for every combination of Q and W, but a better thing to kind of point toward is that a given reaction can have any sign for Q, any sign for W. It's just that the sum of the two have to go to whatever the delta E is for the nature of the reaction. So whatever A to B is, just by nature, they have to give off that quantity of energy. And so the delta E is a characteristic property of the reaction. Q and W is a characteristic property of how the reaction was carried out, what type of system they were carried out in. Okay, so this slide here is kind of getting at the idea of expansion of gases. And so if you have a gas cylinder where a reaction can take place, if the piston moves inward, then that's the surroundings working on the system. And then the surroundings working on the system is that W greater than 0 for the system. So if the system's receiving work, it's like that inward contraction. So contracting inward, absorbing heat inward, is in the positive direction. So the work being done on the system by the surroundings looks like here. And if we allow expansion to take place, if we do expansion, then that would be work being released by the system. Now, I think if I interpret this picture correctly, it's actually trying to show me if this is the initial state. So this is initial, this is final. So we're initially here. I think this arrow here is meant to show like just gravity kind of holding that piston into place versus the pressure inside the container. If we have a reaction take place that pushes that piston outward, that pushing the piston outward is being work released by the system to move that object outward. And so this here would be the system moving that object that's working on the surroundings. So that's W being lost, that's work being lost by the reaction onto the surroundings. And if you do the opposite, if you go from this piston here and you lead to a contraction where the piston moved downward, that contraction here would be W being greater than 0. So it's kind of looking at a before after. So before we're middle, if we expand, if a gas expands, then that is an example of W being negative because we're moving the piston outward. If the piston moves inward, that's the surroundings working on the system, and that has that sign of being greater than 0. Just kind of showing an example of W less than 0, working on the surroundings, versus W being positive, work being done on the system. Okay, so let's say we have a balloon filled with air. It's warmed up, so the air inside the balloon's warm up, and the balloon expands. What is the sign of Q and W for the balloon? So the heat of the air, in order to increase, so in order for it to increase its temperature, its heat has to increase. This is kind of coming from the Q is equal to MCS delta T. In order to increase the temperature, you have to increase the heat of the object. So in order for the balloon to heat up, it has to absorb heat. And then as it heats up, the balloon expands to a greater volume, and that's pushing the surroundings out of the way. And so that's now the balloon acting on the surroundings and moving the surroundings out of the way. And so that's W being released, that's work being released by the balloon. So we have the heat being absorbed to increase its temperature, and then work being released. So moving the surroundings, expansion, negative, contraction would be positive for W. So now the first law of thermodynamics is that energy cannot be created or destroyed, that we can only change the form from kinetic to potential or vice versa, or change the nature of bonds from being weaker versus stronger, and then energy being given off, in the process. that energy is conserved in a process, and we have some different type of systems that we can carry reactions out in. I was mentioning these earlier. We have different types of chemical systems. And so the three primary types of chemical systems are either a constant pressure, constant volume, or a peculiar case of an isolated system. So let's talk about the difference. So an open system is just an open container. So this is just literally like a flask that has a reaction in it. Let's say it's water plus reactants. And then I'll have the products once the reaction takes place. And so this mixture here, we call this an open system because we can exchange energy and matter with our surroundings. So if we need to absorb a gas from air, we can do that. So we can keep a constant pressure inside the container because we're at atmospheric pressure. There's no way that this container can build up pressure. So we can't really move anything. If you're thinking of an open container, it's really hard for an open container to like move the surroundings because there's no surroundings to really move because we're just in an open system. We can also exchange energy with our surroundings, so we can exchange energy and matter in an open system. And then we keep a constant pressure. Again, this is just an open container, like imagine a flask on a desktop. Now, one of the things that we're gonna see is we might want to reduce the energy being exchanged by just putting this into like an insulated cup. So one of the more common forms of calorimetry is just use an insulated cup so you have minimal heat loss of the surroundings so that any heat exchange is kept in the solution, and then you can track the solution with the thermometer. We'll talk about when we get to calorimetry later that this is kind of like what we call like a coffee cup calorimeter if you insulate the cup. Now a closed system is where, imagine we put a lid on this container and seal it up. Now, if you ever get involved in like chemistry or just like research in general, anytime you seal a vessel, you got the possibility that if you build pressure, if that system cannot hold the pressure, it's gonna explode. So you gotta be careful, like in the real world of sealing in, reactions could lead to explosions taking place, but a constant volume container is a sealed container. So this is just a sealed container. And a sealed container obviously has a fixed volume until it explodes, but it has a fixed volume so that the volume can't change. What this means that if you have some reaction taking place in here, that you could build up the pressure, increase the pressure, or the pressure could decrease if there's something that leads to a pressure decrease. So the reaction could lead to a pressure increase or decrease inside the container. So the pressure isn't held constant anymore, but the volume is held constant. And so this closed system still can exchange energy with the surroundings, but not matter. And so that allows the buildup of pressure. And then another type of system is an isolated system. That's where you have a closed system that's insulated. So if you like insulate the system, then the outer surroundings cannot receive the heat. So this is our system here, and then it's insulated from its outer surroundings. So if you're picturing this as the surroundings here of that insulated sealed system, then there'd be no heat loss to the outer surroundings. This is kind of pointless in a way because it's kind of like, it's basically saying if you had a sealed vessel that was insulated and then you put that inside of say we surround this with water, that water temperature would never change, right? So if you're surrounding this here with water and you're tracking the temperature of that water never effectively changes temperature, right? Because you have, like the isolated system can't exchange energy with it. So the isolated system is one where it's not getting any energy from its outside surroundings. It can only get energy from whatever's inside that vessel, and it can't exchange matter with the vessel either. And so those are the three primary types of reaction systems. This is probably a good starting point for next time of like, how do we get from energy to enthalpy? What's the difference between the two? Enthalpy is a big thing, so let's start Wednesday's class after midterm 2 with what this slide's getting at here. All right, guys, that'll do it for today. Good luck on midterm 2, and I'll see you on Wednesday.